Welcome to my Physics 2212 Lab 3 Circuits. The purpose of this lab is to understand how different circuit components interact in a circuit. The circuits in this lab consist of batteries, resistors, capacitors, wires, and multimeters. The physics principles used are the following. The change in voltage through a resistor is equal to its resistance times the current. The sum of voltages in a loop is zero. The current going into a node is the same as the current going out of the node. A brief preview of the results of this lab is that the loop and node rule apply and that the current in the first circuit was 0.02 amperes. The first circuit consists of two batteries, followed by an ammeter, two resistors, and another ammeter. The second circuit is an RC circuit consisting of a single capacitor and resistor. The assumptions made are that the wires are perfect conductors, the multimeters are ideal, meaning they have no effect on current and voltage, and that all components behave as we have seen in class. The system consists of all the components of the circuit, while the surroundings are everything else. For the first experiment, the initial conditions consist of two 1.5 volt batteries, one 47 ohm resistor and one 100 ohm resistor. Our prediction is that the current will equal the voltage divided by the total resistance, which is 3 divided by 147, which is approximately 0.02 amperes. As we can see in the results, both ammeters measured the current to be 0.019 amperes, which is very close to our prediction. The potential difference across both resistors was measured to be negative 3.1 volt. If we flip the voltmeter, then the sign of the change in potential also flips. The following graph shows how the potential changes across the circuit. Initially, the potential is zero. Then each battery raises it by 1.5 volts. Then it remains constant in the wire until the 47 ohm resistor causes a drop in potential. Then it remains constant until it goes through the 100 ohm resistor. After this resistor, the voltage is the same as it was in the beginning. The ammeter does not affect the potential as it has zero resistance. After connecting the voltmeter, the ammeter reading does not change because the resistance of a voltmeter is so large that almost no current flows through it. The second circuit consists of a 1 Faraday capacitor and a 47 ohm resistor. The circuit also included a 10 ohm and a 20 ohm light bulb. Our prediction was that the bulbs will light up immediately and slowly fade out. When we connected the circuit, we found that our prediction was true. The capacitor with the 10 ohm light took 56 seconds to charge and 48 seconds to discharge. With the 20 ohm bulb, these times were 9 seconds and 14 seconds. The predictions and the measured values in both experiments were very similar. This is a good indicator that our assumptions were mostly correct. The slight differences could be due to the following sources of error. Inaccuracies in multimeters. The wire and the multimeter are not ideal. They do very slightly affect the circuit. The batteries may not be fully charged. There could also be some human error. What if you charge a capacitor with no resistor in the circuit? Under ideal conditions, there would be no resistance, which would cause an infinitely large current, thus charging the capacitor instantly. In real life, however, the battery, the wires, and the capacitor itself have some resistance. Therefore, the current is not infinite, although it is still very large, which means it would charge fast but not instantly.